Hi everyone, in this lecture we are going to discuss one example problems related to equilibrium of a particle in two-dimensional systems. So before we started, I would like to review some of the concepts that we have set up in the lecture 11, particularly related to equilibrium equations that we have discussed. Okay. So basically, equilibrium equations in two-dimensional system can be achieved by writing the sum of the forces acting on the particles in the x and the y directions to 0, okay, which is basically these equations right here. So it's particularly mean that in here, for sum of the forces in the x directions, we will have f1x, right, and then we will have plus f4x, right, because they are all going to the positive x directions. And then we will have negative f2x, right, and then negative f3x because they are going to the negative x direction. Okay, as you can see from this force, the direction of this force in here. Okay, and basically we can do this by setting it up equal to 0. Okay, and then with doing the sum of the forces in the y in here, we can write this negative f1y, okay, negative f2y because they are going to the negative y directions, plus f3y plus f4y because they are going to the positive y directions, as we can observe in here, right? Okay, and we set it equal to 0. Okay, alright, and in here you can see that since we only can write two equations, then for any problems we are limited to only two unknowns at the maximums. Okay, so if we have more than two unknowns, then that problem cannot be solved. Okay, let's start with one example problem and let's read the problem together. So a bearing consists of rollers, right? Consists of rollers. So basically, this is the bearing right here, right? Right, and this guy right here, this guy right here, this is the rollers. Okay, symmetrically confined within the housing, right? So basically, this things in here is the housing, right? The bottom one is subjected to a 125 Newton force at its contact due to the load on the shaft. So usually in the bearing we have shaft, right, which is this is the shaft, right, and probably in this case we apply a force going that way in the shaft such that we have a force due to this contact surface over here that try to press the rollers right here. Okay, and due to that force, we know that the force at the contact down here, right, is 125 Newton. Okay, so in these problems you have to find what is the normal reaction force at B and C. Okay, so let me erase this figure right here, right, so that it's not that crowded. So in these problems, right, we know that NA is 125 Newton, right, and we have to find what is the contact force at B and at C, okay, which is NB and NC. Okay, since this is a two-dimensional systems, right, and we talk about particles, then we have two equilibrium equation, which is sum of the forces in the x equal to 0 and sum of the forces in the y equal to 0. And in here we have two unknowns, right? Okay, so the key in this to solve these problems is as long as we can write this equations, we will be able to solve for these unknowns. Okay, and because these equations, it will involve an A, and B, and NC. Similar things, this equation will involve an A, and B, and NC. All right. Okay. It may, I have to say that it may involve an A, and B, and NC. Okay. Okay. So these equations and these equations, it may involve an A, and B, and NC. All right. Let's start it. So in solving engineering problems, okay, in particularly in this course, it is very useful to start by drawing the free body diagram, or sometimes you will call it the force diagrams. So in here, basically the particle is the rollers right there, right? So we are going to redraw the rollers right down here, okay? And then we have the force that we already know, and I will note it with an A right here, okay? Oh, by the way, in here, we do not consider the weight of the roller, okay? Weight or mass is neglected. Okay, so we already know an A is 125 Newton, right? And we have to calculate an B and an C, and I will use red color pen over here so that we know that it is the unknown, right? And B and C. All right, and then it will be very helpful if I can start by sketching the axis, the coordinate systems that I will use. Okay. And then to make it even better, we have to see that in here we have the angle 40 degree. So if I can sketch a horizontal axis right here, okay, since this is 40 degree, this angle right here will be 40 degree. Agree? Okay, so since this is perpendicular, right, to each other, then this angle right here is going to be 50 degree. Okay, and then if I can sketch a vertical line right there, okay, this line in here is perpendicular. Okay, so I know that the angle right here is 40 degree. Since that angle is 40 degree, I can draw a vertical line that this is the 40 degree right there. And I can draw the component of the force NC with respect to the X and Y axis. So this is going to be NCX, and this is going to be NCY. Alright, so we know that NCX is NC sine 40 degree, right? And NCY is NC cosine 40 degree. Okay, in here I haven't included the sine, but later when I do the sum of the forces, I will include the sine. Okay, so when I write the equation, sum of the forces in the X, NB is in the X directions, and then NA is in the Y direction, so it doesn't contribute to the sum of the forces in the X direction. Okay, so the next forces that is contributed is the X component of NC. So in here is NCX, and NCX has a negative directions because it's pointing to the negative Y axis. Okay, and basically we have to set this equals to 0. Okay, to elaborate more, here we have NB, right, and then we have negative NC X, which is and C cosine 40 degree, and this is equal to 0. Okay, so in here we have two unknowns, so we cannot solve these equations directly. Okay, so it's always a good idea to write the second equation, equilibrium equations, which is sum of the forces in the y directions, and in here we have an A because it's going to the y direction, right here. Okay, and then NB has no contribution, right, because it's going to the x direction. And the next forces that is contributed is NC, particularly the y component of NC. Okay, and in here when we write the equations, we have to include negative sign because NCY is going downward, and we set this equal to 0. Okay, so in here we can write NA minus NCY is NC cosine 40 degree equal to 0. So I think I made a mistake earlier, so this should be sine 40 degree, right? NCX should be NC sine 40 degree. So in here we obtain that we know NA is 125, right? And then we move this expression to the right hand side equations. We have NC cosine 40 degree. So from here we can obtain that NC is equals to 125 divided by cosine 40 degree, and in here you will obtain 163.18 Newton. Alright, so once you know NC, we can go back to these equations right here and solve for NB. Okay, so here we can calculate NB is equal to NC sine 40 degree. So we have 163.18 times sine 40 degree, and if my calculation is right, I will obtain 104.89 Newton. Okay, so in here we already solved the problems, and it is always a good idea, right, trying to finalize everything. Okay, and usually I like to resketch the drawing. So right now I know that NC right here is 163.18 Newton, and I know that NB is 104.89 Newton, and I know that in here is 125 Newton, and A is 125 Newton. Okay, I hope this is clear, and thank you for listening.